didn't do a lot of units at ISU in my schooling, so doing conversions is something I do really carefully and second guess myself.
Not a fan of thinking that habit. Wait, how can 1.8 seconds be longer than 30 minutes? That makes no sense.
Yeah.
Then I just go back.
Well, it's official, folks. We're about ready to finish off week 6. So congratulations. We're getting really close to the end here. Well, we're getting close to midterms. But again, the midterms in this class is not a stressful event. We just report what your grade is at the end of that week. So the major announcements are, didn't mean to scroll. Quiz 4 is due today. That one is working exclusively with Z-scores to decide which animal needs to be treated right away at the veterinarian's office. So kind of fun. There's a little bit of high pressure to that problem, I guess you could say. Then we finished off section 5.4. The due date's officially October 12th. I felt like it couldn't hurt to do an extra example on there. This is a question that we'll do a good amount of work on quizzes. We'll do it again as an exam question, and it's probably going to come back as a final exam question. Working with the normal distribution is just one of those problems where it's a major cornerstone of statistics. So because of that reason, we'll do another extra problem just to get that extra practice in. And that will help us in getting through quiz 5 as well. Let me double check. Forgot what quiz 5 was, but it should be the normal model. Yeah, this one's using the normal distribution. So essentially we're doing a different version of quiz 5 just as extra practice. Then don't forget, quiz problems are basically exam problems. I think I did ask that as an actual real exam question a few years back. So I take my old exams and just turn them into quizzes basically to give you an indication of what do the real exam questions look like so you're prepared when you're doing them for real in an exam setting. Well, that's where we're at so far. Any questions at all, folks, before we get started? Okay, well, let's dive right in. So we're handling the extra example. After that, we'll change to chapter 6. This one's a little bit, I'd say mid-length or slightly long, but not long enough to break up into sections like 5.3, 5.4. So we'll take some time on these notes, probably a couple days. I'd say we might finish it maybe Wednesday of next week, but we'll see where we end up. It requires extra work with the TID4 calculator and getting things to work out just right. So it's kind of a touchy section for those reasons. But once we get a handle on what's going on there, it's just like any of the other sections. Well, let's jump in then. In section 5.4, the extra example, this is what it looks like. It's a reminder that snow is coming eventually. This is autumn that we're already in right now. The problem
after you're done with your gig.
Open mic. Got it. So the problem starts off by saying in Rochester, New York, if I'm pronouncing that right, I'm not sure, it averages 21.9 inches of snowfall for just the month of December. That's quite a lot to shovel if you think about that. The distribution of snowfall amounts is normally distributed, we are assuming, with a standard deviation of 6.5 inches. So first thing we want to do is state values of parameters. And part of the work on here is to use the correct symbols for each one. Mostly that's for us to just kind of recognize in our mind's eye, what do we mean when we say population mean, and what is the symbol that we use along with it? So we have a value for mu. We have a value for sigma. Anyone have a value for one or the other? Any volunteers to fill that out? Good call. The key here is where they said average. They could have said there's a mean of 21.9 inches, but we always assume that average and mean are totally synonymous. So that's enough information to say here, 21.9 inches. Well, if you get one down, then you're all set. There's only two parameters, so knowing one gives you the other. Standard deviation here, we could have said population standard deviation, but if we're not modeling with the normal distribution, it is assumed. So over here, we'll put sigma is 6.5 inches. So lots of variability in the amount of snowfall. Now, knowing that much information, we can ask some interesting questions about what could happen in a generic season. So if this model is accurate for, say, 2024, we'd be able to determine the percent chance that Rochester will experience 10 inches of snowfall or less this year. So that's the question we have to answer. Part of this getting full credit is we do have to include a graph. And again, that's something you would want to do anyways. That's how we would award partial credit if you have the wrong number on your answers. So the graph doesn't have to be anything special, just a way for us to organize the information. And this is not a very good graph, but it'll do the job. You don't have to put the N here, but this is just a reminder that we're modeling with the normal model. So N is paraphrasing that. 21.9 tells us that the center is right at 21.9. And finally, standard deviation is 6.5. So when it says include a graph, you could put the N 21.9, 6.5 if it helps out, but we're mostly looking and concerned about this. We have to add some information to the graph. 10 inches of snowfall would go somewhere probably around here. It's not perfectly exact, but it's definitely to the left at 21.9 and a good amount to the left since 6.5 standard deviations do say it's approximately 5. 2 to the left, getting close to taking 10 away from 21.9, which puts you about here, close to 10. That's all just kind of roughly estimated. It doesn't have to be perfectly placed in the end of the day. So here's the value of 10. At this stage, we have to decide which way are we shading by the red dot? Do we shade to the left or do we shade to the right? Sorry, say again? Exactly. If it says or less, that's shading to the left. So this is the diagram that I would expect. The curve, a value of 10, and the shading as well. So that gets you good credit on getting the graph down. Now we just indicate what we're putting in the calculator. The orange pen is just my way of giving extra detail in the notes. It's not something you have to write down under paper. It would be lots of writing after a while. But we have to know what is the lower bound that we're putting in the calculator. Anyone see where it is or what the number should be? Exactly. This is going to the left forever, just like you said. So negative 10 power 99. Let me put actually over here. Then we go up to the 10 value. This is what we call the upper bound, or the calculator just refers to it as upper. Finally, input 3 is mu, input 4 is sigma. So that's the organization of what's going on in the calculator. Back to the calculator, we worked pretty carefully with this, and we're still going to do it. It's only our second time doing the normal model. So first things we have to hit is the second key and the bars button to pull up our distribution. The next question we have is, which function do we use? We're only working with two, inverse norm, normal CDF. Any volunteers for the correct function? Turns out the wouldn't be inverse norm on this one. Good call. Yeah, it's the percent that indicates. So I think that's a good way to think about that. If you're focusing on the percentages, then you'll know every time a percentage is missing, you're using normal CDF. So watch out for the percentages and say on these, use inverse norm. So this problem will be normal CDF. So we hit option 2. I'll just press enter on the calculator. And now it's pretty much as fast as you can type. Now notice what my calculator is saying. It kind of just resets every time I turn it on. So you probably have your old result. But -1 e power 99, that's just saying -10 power 99 in the calculator's way. So calculator is expecting these kinds of results when you're using the normal CDF. I'll leave that in, or, well, no, it just looks weird. I prefer to usually put it -10 power 99, just because it just looks familiar with how we do it normally. So I'll keep that pattern going. Upper value is the value in question, 10 inches. The mean is 21.9 inches. The standard deviation is 6.5 inches. So altogether, let me add just one more thing to the axis. This is snowfall. in inches. So we're asking the question of, if they average about 22 inches of snowfall, what's the percent chance they have like the easiest December ever in Rochester, New York? 10 inches of snowfall or less. This will do the job for us. So hit enter here, and here's what we get. Really low percentage so far. Well, this is a probability, not quite as a percent yet. So either shift the decimal mentally in your mind's eye or just go times 100. I should go like this so I don't get my digits mixed up when I go to grab the answer. And I made the rounding a little bit more sensible. Usually if you're quoting a percent, you would do 2 decimal places. If you're giving a probability, usually you would give that one 4 decimal places. That's why the rounding kind of seemed weird on the last set of notes. But there's our percent. To the second decimal place, that would round up to 3.36%. So 3.36%. I don't know how I pulled that thing up. Weird. So there is a 3.36% chance that, I'll just say they, for everyone in Rochester, New York, just to paraphrase a little bit better, they will get 10 inches or less. Well, any questions, folks, so far? Okay. By the way, the wording on these kinds of problems are kind of interesting in a way. You might have noticed in your back of your mind a weird nagging thought that if I said 10 inches of snow, or let's say this was rewritten as less than 10 inches of snowfall, and I'll fix that in a moment. Suppose that was the question. Strictly less than 10 inches of snowfall, not equal to 10 inches or less. The calculator can't actually distinguish that, and neither can the normal model. So one thing that's really weird about the normal model is whether this was implied as a strictly less than 10 inches exclusively, or if you're implying that it's a less than or equals to, so 10 inches or less is implying less than or equals to, it makes 0 difference in the calculator. That's really kind of weird in a certain sense. Another thing that's weird about this normal model that you might have noticed is there's always an interval. No matter what, there has to be an interval. What I mean by that is I can't ask you the question. I'll delete this in a moment because we can't ask it and get a serious number. We can't ask what is the percent chance of exactly 10 inches. I mean, we could ask it, but it's a weird question. Here's what would happen in the calculator. If you say exactly 10 inches, the shading goes funny. It's just that one vertical strip, that line right at 10 inches. A line has 0 width, right? So the area would be 0. That means the percent chance would also be 0. It would mean the upper value and the lower value are both 10. If you put all that in the calculator, here's what happens. Second bars, go to normal CDF again. Let's suppose the question was, what's the probability of exactly 10 inches? The lower would be 10 inches. The upper value would be 10 inches. Hit enter on all that stuff, and it's probability 0. 10 inches is not special here. Any question that involves one single number is probability 0 if you're using the normal model. That's a defect of the normal model in a certain sense. It's surely non-zero to get 10 inches exactly, right? That could happen. But if you're using the normal distribution, single number is always probability 0, no matter the context. So this is just a reminder that this is a mathematical fiction, really. It's a function that we just invented to fit data really well, and it has its own shortcomings. This is one of the shortcomings. The only questions you can ask have to have an interval somehow wrapped around it. So 10 inches or less makes sense. Exactly 10 inches has a 0% chance by this model. Very strange, but still it's a great way to try to model things in reality, even if the model is imperfect.
If
Yeah.
the problem had asked us for less than specifically 10, would in the calculator we put 9.99999 and get a close estimate to that? That would be less than, or that and less 2. Would that be the answer to that question?
It'd be a good way to think about it, absolutely. So if we go back to the calculator just to think about that. Let's say again, they said here, less than 10 inches. So exclusively less than 10 inches is what we're trying to do. Then we would say lower, -10, power 99. Then go down here. Well, let me try again. It was 10 inches, so we'll go 9.9. But the trouble with 9.9 is if you say less than 10 inches, oh, that would have been a real syntax error is what it would have said to that. Thank you for spotting that. So if we say less than 10 inches, so that's the question that we're trying to address. On the number line, we can think of 10 inches being right here. Now the trouble is 9.9, you zoom in large enough, it's out here. Less than 10 inches involves numbers that are going even closer, right? So you'd have to put in another 9. If you zoom in on this number line close enough, 9.99, there's still always a separation, a big one. So you might decide go, well, lots of 9s, right? Well, as soon as you do that, yeah, we still have the error, and this number is eventually just going to round up to 10 anyways. Let's suppose we just put in that many 9s. I think it was like a dozen of them or so, maybe a little bit more. Let's hit enter, run through the numbers, times 100, and we get 3.36. Exactly, and we didn't have the most accurate number, right? Because, well, if you're strictly less than 10 inches, there is more and more 9s that are going up in here. That's a bit of a problem in the calculator because eventually it's just rounding it to 10 inches anyway. So again, that's something that's weird about the normal model. If you say less than in your problem, you get one answer. If you say equal to 10 inches or less, you get the same exact number. Really pretty weird. Other questions about that so far? Okay, so when you go to deal with these kinds of questions, oh, didn't need to delete too much there. There we go. Try not to worry too much with whether it's saying less than, or equals. When you're writing out answers like these, it's also not as important, only because the normal model doesn't care about those kinds of things. You get the same exact answers either way. Other questions so far? Okay, let's try out part B. Part B says, what is the percent chance that Rochester will experience between 10 and 20 inches of snowfall this year? Include a graph, round to 2 decimal places. Really, it's the same kind of problem as before. We're going to use normal CDF, and I should fix my shading before I get too far. It's the same as before, except the lower value is going to be the lower number 10. Upper value will be the higher value, 20 inches. So this is what the graph would look like this time. I'll just do a really rapid graph since we have more detail than the one right above. So here's 21.9. We're putting in between 10. I'll leave that there again. You know, looking at this a little bit more closely though, 3.36% means maybe 10 should have been a little bit further to the left as well, but I wouldn't get too hung up on making this perfect. It's just, again, to organize information. So I'll make it about the same. Here's 10 inches. 20 inches looks like it'd be about up there, close to the mean. So whatever this number is, I would expect it's getting kind of close to 50% of the information, or somewhere above 40%. Any questions with that so far? Okay, so in this arrangement, whenever you're giving numbers one and another, so you're between, it's a little bit easier to put in the calculator. You can say right away, input 1, lower, is just a lower number cutting off the area. Input 2, upper, is just the larger number cutting off the area. So I think it's a little bit more logical with those kinds of questions. Well, input 3 and 4 is always the parameter of the model, so I'll leave that there for the next follow-up questions. Let's go second. Stat is not the right way to go, my mistake. If you're in the wrong menu, you can always hit second, quit, and it takes you out. Let me try again. Second and bars gives us where we want to go. Press 2 for normal CDF. And now the lower is just 10. upper is gonna be 20. It remembers everything else we put in, so now we just hit enter a bunch of times. And that's our percent, well, that's our probability so far. Well, this was a lot lower than I thought it would have been, so probably I put my 20, should have been a little bit further off to the left. But is that what folks are getting at the moment? Awesome, that's good to hear. So let's go times 100. Rounding this to 2 decimal places will give us 35.15% chance. So 35.15% chance. That means it's a pretty typical year. About a third of the time, they're getting between 10 and 21, or excuse me, 10 and 20 inches of snowfall. Quite a lot to deal with. So let's say here, just to give an interpretation to this number, there is a 35.15% chance they will get between 10 and 20 inches of snowfall. Again, that's for the total month of December. I almost feel bad about them working through these kinds of problems. Well, any questions at the moment? Okay, now let's look at part D. They're asking, what amount of snowfall describes the 1% of worst cases for the month of December in Rochester, New York? Include a graph. When it's time to round it to 1 decimal place. I don't think I could ask this as an exam question, however. Anyone see what the problem is with that problem as an exam question? Well, it's worded kind of ambiguous. Yeah, it's kind of worded wrong in a real sense. What does worst mean? If you hate snow, worst means too much of it, right? But you could love snow. A lot of people in Idaho just adore snow. They want to go skiing, snowboarding, things like that. So a person could read this problem and decide they're talking no snow. That's the worst case for them. So I couldn't really ask this kind of question. I'd have to be more descriptive. Let's go with the thought that worst cases just means more snow to deal with. Does that sound right to folks? Okay, that will be our interpretation of this problem. And again, in a real exam situation, this would be made less ambiguous. But let's say right here, by worst cases, we mean high amounts of snow. So now that we know that, we can actually write down the model and know where to place things. We're using inverse norm because they gave us a percentage, 1%. But that means we have to be really very careful with this problem. We can't actually use 1%. We have to convert that to a decimal. So that's the first thing that we need to worry about. So 1% converts to 0.01. Now the horizontal axis, let's bring back the unit. It's snowfall in inches. So that means worst cases means high amounts of snowfall. Going to the right, let's put the center in here just to have some protection and making a mistake. So worst case means take 0.01 and place it way out here. It's really even further to the right, but I put it in a spot where I can just see it a little bit better. Again, don't worry about full accuracy in your diagram. You're just organizing information. Here I'll put X, and the question is, what is the value of X? So we're solving for that value. Here we have an area, which is equal to 0.01. This is where it gets a little bit tricky for us as a class, because there are multiple different kinds of TID for calculators that people are using. So if you're using the more fancy one that probably has like some kind of LCD display, lithium battery, that kind of thing, I think it's like the TID4 Plus CE edition, then you want to select right tail and put in the area of 0.01, and you should be all set. But for everyone else, it's almost not fair, but it's just the world we live in. Things are not always totally equal. If you have,
The inverse norm, sorry.
yes, this would be inverse norm.
Oh, yeah. Sorry.
No worries. So for everyone else using the TID4 Plus, let's put down this extra warning once more, because this could be really kind of confusing in my opinion. The TI 84 Plus meaning just the ordinary one, only accepts area to the left. Deserves an exclamation mark for sure. That means I can't use that area. Let's go ahead and try it anyway, because it's good to see one more time what it looks like if we do it wrong. It's so easy to do sometimes. So if I actually give area to the right, in this calculator, we'd go second, bars, go to inverse norm, area. It's natural to put in 0.01 since that was the question. Mean 21.9. Standard deviation 6.5. So this is what it would look like, but if you put your center on your diagram, I always highly encourage that. It's great protection against making this kind of mistake, because this is the answer you're going to get. About 6.8 inches of snowfall. Well, that doesn't make sense here. That's on the other end, way over here. So what we have to do instead is, if the area was 0.01 here, anyone recall how to get the area over here? What should it be? Exactly. We just use the complement rule that says total area exactly 1. So 0.99 goes here. And you can check it even in the fancier CE edition of the calculator. If you set your tail to the left tail, give it 0.99, you get the same answers. So if you don't want to worry with left tail, right tail, you could always just leave it on left tail if you would prefer. And you're always doing the problems exactly as we're doing in this calculator. So let's start with the inputs then. Input 1 is area to the left. Always deserves good emphasis. The area to the left is that 0.99 that we're giving it. And input 2 is mu. Input 3 is sigma. So we just use those values up here that we stated. So let's try it again. Well, maybe let's take a step back and just look at the problem once more. So to paraphrase what we're doing here, the moment they gave us a percentage, it meant we're solving an equation, a real mathematical equation. The calculator's just doing it for us, essentially. That's the only reason we're using inverse norm. The percentage was given to us. Then the second problem was that percent 0.01 goes here. We had to convert it to a decimal though. So if we gave it an answer of 1, we're getting the wrong answer again. Then we had to get area to the left. So we took 1 minus the 0.01, and that's what's going in. So putting all that together, hit second, bars, option 3 for inverse norm, area 0.99. Since that's our area to the left, we already have our parameters imported. So just jam the enter key. And this is your output. To 1 decimal place, this would be 37.0 inches. It's like I ran out of space down here. So here's our last bit to write in. X equals 37.0 inches. That's pretty extreme. If we got that much in Idaho, a lot of people would be pretty upset, I'd say. I don't think we'd get that much for an entire month of December. Usually our snow season doesn't even really get going in December in the first place, at least not these days. So it's 37.0 inches, just or more. So that's the thing about this question. When we just are trying to describe the 1% of worst cases, X is just the lower cutoff. It could be 37 inches or 50 inches or 100 inches. Anything above that is describing the 1% of worst cases in Rochester. So 37 inches or more describes the 1% of worst cases. Well, we did it, folks. That was our bonus problem, just getting extra practice on this. Was that helpful on seeing how the calculator interprets all these pieces of information? Awesome, glad to hear that. And again, if you're working these on the homework problems or doing this as a quiz problem, if you're getting weird numbers in your calculator, definitely include a graph. Well, I mean, it's part of the credit, because a lot of your questions could be resolved just by looking at the graph. If it still is not coming out right, well, you can send me a screenshot of your work, send me an email, drop in the office hours. I'll be happy to help out. A lot of times it's just something weird going on in your calculator. And if it's an inverse norm problem, usually what's going wrong is we gave it a 0.01 when we really had to give it a 0.99. And before I save the notes, let me circle this one just to convey that's what we actually had to use. Any last questions then before we close these notes? Okay, give this a minute to save. There it goes. And these notes, 5.4, the extra example is just right under here. It's also in the Blake lecture notes as well. So we're changing gears, folks. We've done a lot. If we go backwards in time now to right around here, in chapter 3, we were handling, let's see, 2 categorical variables all at once. Chapter 4, we did a categorical variable together with a quantitative variable. So we're mixing variables in that sense. Chapter 6 is, or chapter 5 is just the normal model, modeling with that normal distribution. But now connecting the pattern, chapter 6 is 2 quantitative variables. So chapter 3 was 2 categorical, chapter 4 was categorical, quantitative. Now here we're dealing with 2 quantitative variables at once. So that'll be kind of exciting. Let's open those notes up and take a look. Didn't mean to make it that big. Sorry, let me fix my windows real quick here. Okay, so here's how the problems or the notes start out. If we're dealing with 2 quantitative variables, a really excellent way to display them is going to be the so-called scatter plot. Hey, you know what? Maybe before we just jump right into these notes, let's do a bit of a warm-up on this. So let me push this stuff to second page. There it goes. It's on the second page. Let's call this just a warm-up problem. Warm up for the entirety of chapter 6, I guess you could call this. So if we're dealing with, like we said before, 2 quantitative variables, then we need a great display for displaying all that information. First of all, let's say what the information might look like. You might have something that goes like this, a table going vertically. In the problem down below, my table goes horizontally. So either way you display it, you have to have 2 quantitative variables for sure. Let's just call it X and Y. So generically, let's say 0 and 1. So this would be our first set of observations on the data set. Then maybe -3, 2, second set of observations. 5 and 6. And how about -1, -4, and 0, 2. So pretty much just random numbers is what I put on there. But that's how your data could come in if you're dealing with 2 quantitative variables. So notice we have now both X's and Y's. In the prior chapter, the author used Y all the time to describe the data, describing the mean as Y bar. This is part of the reason why the author does that. It's kind of annoying at first, especially when your calculator gives an X bar, but there was a purpose to all that madness. We call X in a mathematical class the independent variable. In statistics, we don't use independent variable as often because that could have a different meaning. Independence as a mathematical function and independence as variables are not completely the same concept. So instead, we call this, to clear up that conundrum, the explanatory variable. It's going to be the variable that explains why Y is changing. So Y is going to be referred to as the response variable. And a great way to display these data is, once again, the scatter plot. This is what a scatter plot would look like. It could be an entire XY plane. That's a great way to display it. But oftentimes your scatter plot could look just like this. A window just giving data. So because it's a warm-up problem, let's not go for the more confusing thing. Let's do something more familiar and just go with the ordinary XY axis displayed in this kind of way. So the horizontal axis contains the explanatory variable. The vertical axis will contain the response variable y. Now all we're doing is plotting points. But this class didn't have any real prerequisites for math. So think of the warm-up that we're doing now is more just getting everyone on the same kind of page with what we're about to do. Some people may have no trouble with this. Other people might feel like, well, it's been a while since I plotted ordered pairs. And that's what these are. When we have two quantitative variables, each row is for one individual, just making two measurements on that same individual. So we plot 0, 1 as a pair of data. What we do is 0 means go to 0 on the x-axis, right where the axes meet. 1 means go 1 tick mark up. And that's our first data observation. We ordinarily wouldn't put 0, 1 to describe it like this because the display would get way too busy. So in a scatter plot, it's just going to be the point. Does that make sense, folks, on how we're plotting these? Okay, again, this is kind of a get everyone on the same page type of problem. So let's do this carefully. -3 means on the x-axis, which direction would you go, right or left?
Left.
Exactly, the negative direction is just saying go left, 3 tick marks. Then I have, well, let me take a look. I should be able to fit that in. So we went -3, now we have to go up 2. Here's a height of 2. Or let me make sure this is actually going to fit here. About, that should work, yeah. So there's our second point. It's at coordinates -3 in the x direction, and then up 2 in the y direction. So 2 data values. Let's keep on going. 5, 6 means 5 right. 1, 2, 3, 4, 5. Up 6, 1, 2, 3, 4, 5, 6. That's what I was kind of worried about leaving my axis. And notice I'm not plotting this perfectly. I do have some issues on my graph. For example, that scale right there by the red dot, ideally it'd be maintained everywhere. But if you're doing this by hand, I'm not as worried about that. We'll make the technology plot a lot of this for us. So this is us again, just practicing. So here's the point at 5, 6. X1 is -1, -4. Over here, we move left, so that's at -1. -4 now means go down. 1, 2, 3, 4. And we land on that point there. So 1 left to go. 0, 2 just means don't go any direction on the x-axis, stay at the origin, and then go up 2. So there's our points. Kind of a weird arrangement of points right here. But any questions, folks, on producing those? Okay, so that's pretty much what we're trying to do with these data. We're trying to get a nice display with them. Not too different than when we, for example, in prior chapters, think chapter 2, as well as chapter 5, when we had one quantitative variable, we hoped for displays that looked like this. We have something that's reasonably symmetric, and we can say that that display, choose a fun color, this can be modeled by the normal distribution. Reason being is our data is fairly symmetric, it's unimodal. If we try to fit a normal curve to it, won't be perfect, but you know what? That would do a decent job. A normal model centered right about there. So that's with one quantitative variable. We modeled the data using a normal model, did some calculations just earlier today, and we showed how that goes. So what about 2 quantitative variables? We want to model these data as well. And the way we'll do this is now in chapter 7. Yes, chapter 7. What we're going to attempt to do is take these points. Sometimes there'll be a lot of points. Imagine a cloud of points. We wonder, is there a pattern to these data? And if there is, the pattern we're looking for the most is a linear relationship. If we can get a linear relationship going, then we can use the correlation coefficient. So that's where that's coming up. So what would a linear relationship look like? We're attempting to draw a line that's going to get as close to all the points as possible. So now if my line looks like this, would you agree that's doing a terrible job? We could try to make it fit through as many points as possible, but if I try to intersect here, I'm missing all of these. And the slope of the line matters too. I would say maybe that's doing a little bit better, but if the line goes, say, like this, well, more like, say, that, well, it could do a good job, but it doesn't feel like it was doing as good as the original line. Let's see how we feel about that. So here's my new line that I slanted off in a weird direction. Control Z, that's the old line. Which one would you say does better, this one or the prior one? I'd say maybe. It's kind of hard to say. They're sort of close, but those are the kinds of things we're trying to do. Just like we try to fit a curve over a symmetrical histogram, in chapter 7, we're not trying to fit a line through the data. That's kind of hard to do, but the good news is the calculator has no trouble whatsoever with this kind of thing. So this is a preview then. In chapter 7, we fit, let me make that a sentence. In chapter 7, we fit this is called regression line to the data. So I'd say the big takeaway with our warm-up is just getting familiar with what the points are, how to plot them, and if you're just looking at a point, pulling out coordinates, as well as it's looking ahead. Don't worry about too much about finding equations of line or plotting lines by hand. We're not doing too much of that mathematical stuff, but we have to know what the line is saying, and so we'll be looking at lots of lines when we're in chapter 7. Well, any questions at the moment, folks, with the warm-up information here?
When we're making the regression line, do you want to hit the most points, or do you want to be in between, like by the center of the dots?
Kind of what you said in the ladder. We're trying to get to the line that is closest to the most amount of dots as possible. And if you're curious on how that's going to go, here's another preview. It's going to be this idea. Once you put any line down, you can measure distances that look like this. So that red line is the distance between the actual data that you had and what it would be predicted as through the line. Here's another red line. That's a huge error. Over here, the error is really small. On the next one, a little bit bigger, kind of a small error. So the line that does the best job will take all these distances, it's going to square them, and then try to minimize the sum of the squares. Lots of weird stuff going on there. So that's what the regression line is attempting to do. Let's say that here, just because we wrote it out. The regression line minimizes the sum of, here's a new word, this is called the residuals squared. When we say a residual, we're meaning that distance. So that is a residual. Well, this page got a little bit busy, but there's lots of things to talk about. As soon as you put down 2 quantitative variables, the whole game changes. There's a new way to analyze, new way to view, and this is what we're going to start taking a look at. We're not going to be doing the line in this section, but when we talk about correlation, we are looking into the components of how to actually build that line. So we're getting really close already in chapter 6. Any questions, folks, so far? Okay, that's kind of overwhelming as a preview. So if you're coming back to this, it might be better to actually see it in the video when elements came in step by step. Reading that as a complete picture, I mean, I can kind of tell what's going on, but it's almost too much stuff at this point. So sometimes the videos are superior to the actual raw notes, just depending on what you're doing. But let's go down and let's start this section officially. So like we were discussing, scatter plot is going to show the relationship between 2 quantitative variables. So that's going to be the information we're dealing with for everything in chapter 6 and 7. So next, once you have a scatter plot like we were describing, your variables have different roles. Y variable is going to be the response. And X is going to be what explains how Y is changing, explaining the response variable. So here's our example to go along with those lines. This says algal blooms. That's just a weird word. I'll just say algae. That just seems a little bit easier to say. They're officially saying algal blooms or algae blooms have negative effects on ecosystem by dominating its phytoplankton communities. And it goes on to say, this algal or algae, that's an interesting word, is a nuisance algae infesting many parts of Northern Europe. These have all sorts of bad consequences. Sometimes, I think you might have seen in the news, when there's an algae bloom, like say the Gulf of Mexico, essentially all the fish die since the oxygen just gets depleted out of the water. Crazy things can happen with this stuff. So it makes sense that people would want to try to control nuisance algae. So here's what's going on next. They say, a research team examined the relationship between. Now it already sounds like two quantitative variables if you say relationship between the net growth rate of this algae and the number of, here's a new organism, Daphnia magna grazers introduced in this test tube. So this organism looks like, this is referring to the number of grazers here, but that's what's eating the algae. So if it's an effective consumer of that algae, then maybe we can control it using that thing. It says next, the net growth rate was computed by comparing the initial and final abundances of the algae in the experiment. So let's take a look at the data. What they did was they put algae in a test tube, and then they introduced something that munches on it. They introduced one grazer in a test tube, not one. The next test tube had two grazers, 3 and 4, and so on. Here's the net growth rate of the algae. It says a negative value indicates the decrease in the abundance of that algae. And it kind of makes sense. If there's only one thing eating it, then the abundance went down by that net growth rate. If you put a whole bunch of grazers in there, it should be going down by even a whole lot more. So that's what's going on with the data so far. But here's where it gets a little bit tricky. We want to know what is the response variable and which one would be the explanatory. Any volunteers in class or over Zoom for either one of those? Among these two variables here, the number of grazers munching on the algae, and the net growth rate of the algae, which one would you say is explaining the other? Which one would be the explanatory variable? Let's see. Not quite. I think it's backwards on this one. But let's see if we can think of why. Essentially that, yeah. If we're thinking it's going down because of something we did, that means it's going down being explained by how many grazers you put in the test tube. So we'll say here, the explanatory variable, and this is really tricky. This is going back to the same idea of it's all about the context. So you have to think about the context really hard when you do these kinds of problems. In fact, if you're doing this, it's not a bad idea to just pull up this thing. I mean, that's abstract. That's a scientific name, right? You should be able to right-click it and go to search. I don't do this often, so let's see what this pulls up. Looks like it's some kind of, maybe a single-celled organism of some type. So this is what's eating the algae. And then, well, now that you have a picture in your mind, it makes everything a little bit easier unwinding this context. So that's not a bad idea to try when you're reading these kinds of problems. Let's do it again for this one. This is the algae. And what do we have? Oh, hang on. Looks like the same picture. Oh, I forgot to click on the right thing. See, that's why the context is important. When I was thinking about grazers, I highlighted this thing. That's back to the algae, right? Where's the grazers in this context? There it is. Thanks for finding that. I missed that one entirely. I guess we can hit it with some highlighting. So this is the thing that's munching on the algae. Let's look that one up. That looks a little bit more accurate. So this is your picture in your mind's eye, kind of nasty looking. Whenever we say grazers, that's what's eating the algae. Oh, wow, you can click on it and it puts a screenshot in your report. That's kind of cool in a way, but that's maybe a big distraction. It's just cool to see what's going on. So this is eating the algae. Let's get back to where we are. And that's what's explaining why the algae is growing less and less, the more of those critters you're putting in the tank. So with that picture in your mind's eye, this becomes the explanatory variable. Number of razors. And the response variable becomes net growth rate. So that's that variable right there. Any questions at all, folks, on identifying those two variables? Okay, well, now that we have that, we want to construct a scatter plot. And some people might have gotten started already. You can complete this one pretty fast. There's 4 pieces of paired data. But you know what? We have technology available to us. Let's practice doing the technology scatter plot in our calculator right away. This will be helpful for the homework. So I'm not going to ask you to plot lots of stuff on exams and such, but in the homework questions, you are going to have to identify the correct scatter plot given data. One way you could do it is just by plotting your own scatter plot. But when there's a lot of data, that can be tedious. So let's take advantage of the technology. Scatter plot from the TI-84 is kind of tricky, so I'm going to be upfront with you about that. You might notice that there are some documents here. If you're going to do your scatter plot for the very first time, definitely check out these notes. Again, this is not as necessary for exams, but that one is. We may have to calculate a correlation coefficient on an exam setting, so we'll look into that document as well once it becomes relevant. So that link on Moodle just takes you to this web page. And let's just follow this to the letter. So if we're going to do a scatter plot, I get kind of rusty on this myself if I haven't done it in a while. It says the first thing you need to do is go to second, stat plot. Let's do that right here. Hit the second key. The stat plot function is right here, your top row of functions. Takes you to this menu. And if it's a brand new calculator, probably everything is on. If you bought this from maybe a former student as a used calculator, some of these could be turned on. But what we need to do is turn on one of these plots, just the top one. So you can scroll around, but stay just on the top one right here. We're still on step 1, and hit enter. So mine's on off right here. Hit enter right here until the on is flashing. That looks good. And it already knows what I want to plot. Down here under type, that one should be the one that's highlighted. But now you might notice if you are just bored and you want to play around with the calculator, you could do a time plot, a histogram, a box plot. That looks like a box plot again. I'm not too sure the difference between the two. Oh, I see. Yeah. So just a more descriptive box plot here. That one looks like a line graph of some kind. But this is what your calculator should look like at this stage. So we're done with step 1. Any questions, folks, getting that turned on?
How do you get to the stat button?
That was the second button, and then the Y equals button. Other questions at the moment? Okay, so now that we've done that, you may not have to do this step, but again, just depends on if your calculator is brand new or if someone's been using it for a while, or like if you lent it to a kid brother or something like that, it can change a whole bunch of weird options. So you have to go to Y1. That means you're just pressing the Y equals button. It should send you to this list, and you want to clear out any functions. That's already been done in my calculator, but you might have had something like this. Questions first?
Yeah. If I didn't enter.
Let me go back to that prior window to answer that. So I was at this one right here, right? With everything turned on. Then on step 2, it says go to Y1, but what they mean is just press Y equals right here. So press the Y equals button,
Okay.
and then that should come up next.
I've got all kinds of colors on mine.
Oh, that's kind of cool. Well, there should be nothing there in the other day. So if there's something here, just use the clear button to wipe it out. So everyone's screen should look like that. If there's any function in there, it could throw everything off. It's kind of frustrating. Any questions, folks, to this step? Okay, at this stage, it starts to become familiar. Step 3 says, hit the stat button. So right at this menu, just hit stat key. Go to the edit key or the edit button. We're already there. And enter your data in L1 and L2. So now we have paired data. We're using both L1 and L2. That's kind of exciting. Let's hit enter here. Now back to our data. This is where it becomes critical to know which one was explanatory and which one was response. And there are hints here. It is typical that your explanatory variable comes first. And I don't try to mix that up. That'd be weird. And we try to display the data in a way that makes the most sense. So if it's horizontally displayed like this, your explanatory variable is usually the first one. If your data looks like this, your explanatory variable is probably the first column. So, well, we know for sure the explanatory variable goes here, but that means in the calculator, this is L1 for explanatory, and the response variable is L2. So that's the one thing we have to be really careful with. If we mix this up, our display will look different. So L1 is not too bad, just put in 1, 2, and 3. And 4. And you could just hit right arrow, and it brings you to the top of the very next list. Here we'll go a little bit careful. Don't forget, you have to use the actual negative key here to negate your number. Negative 1.9, enter. Negative 2.2, negative 4.1, negative 4.3. So you should have a balanced list, 4 pieces of data on one side, 4 pieces of data on the other side, and we're almost ready to go. But let's go back to the cheat sheet. This is not straightforward sometimes. So option 1, you don't do every time. You set that option in the calculator and it's going to remember that. Option 2, you wouldn't do every time either, unless you use the calculator for some other purpose. Just make sure you cleared out that function. Usually you start at step 3, import your data, like we have right here. Step 4, this is where we're going to actually plot it. Turns out what you need is the zoom key. So hit the zoom button right on this screen. Pulls up a whole bunch of options. What we need is option number 9, zoom stat. So if you scroll down here, there's zoom stat. Or you could just press the button 9 and it goes right to that option. I guess probably what you would do if you're using scatter plots all the time in your calculator. So hit zoom stat, enter on that, and that's our display. Notice, like we said before, you don't see an X and Y axis. What you see is just a viewing window that contains the extent of all your data. But you can do kind of fun things here. The left arrow keys should work. So hit left arrow. Well, kind of did. You can move around and find the coordinates of those points. So the coordinate of that point is at 2, a little bit of change. The Y value is at negative 2.21. Let's take a look at our data. At 2, we get negative 2.2. Yeah, that looks about right. We're just about at that spot. Yeah, I was using the arrows here. I think there might be a better way to see your points though. Let me try this. Trace. If you press the trace key, it's putting the cursor right on your data values. So moving around, left arrow, right arrow, it's just showing you the data all over again. Sorry, say again, question? Oh, weird. So if you get a mismatch, let me see if I can re-engineer that. It sometimes means one of your lists has more than one number. So if I put a 5 here and go zoom, option 9 for zoom stat, that's when I get the dimension mismatch. So it might mean something interesting about the data there. You could go back by hitting the stat button. Oh, I guess I have to hit enter to quit out of that option. Then go stat, edit, and deleting that value there should make it work again. Yep, absolutely. So let's recap. If you're going to do a scatter plot, then if it's for the very, very first time, you have to check option 1 and option 2 here. Make sure all that's working. Any questions, folks, on getting either the step one or step 2 working well? Okay, so once you have that, next thing you do is you just go back to your problem, hit the stat button, hit enter, and just put in your data in this way. Critically, make sure L1 is your explanatory variable and you're all set. After your data is in, you just hit the zoom key. You go down to option 9 or just press 9 on the keypad. Usually I do it this way just because it's more visual to see. We went down to option 9, zoom stat. Hit enter here, and this is what we were going for. And again, the reason for doing this in the calculator is not because we're going to be doing this all the time on quizzes or exams. I don't think I'll ever do this, ask this on a quiz or exam. This is more to help out in homework. In the homework, they're going to give you a bunch of data, and they show you multiple choice of different scatter plots. But if you like, this is a good option to do it instead of working it out by hand or just trying to eyeball which plot looks incorrect amongst the list. So here's our display. It says construct a scatter plot. This is not how you would answer a question on a quiz or exam, but once again, this is more for the notes. I'm not going to ask this as a quiz or an exam problem. Well, we did it, folks. We have 2 axes here. This axis going this way is number of razors. And this axis going this way is the net growth rate. So what we really want to do is the researchers here, they're going to say, well, what would happen in general here if we were to introduce these organisms to the wild? Well, they need to now model both of these variables, 2 quantitative variables at once. They're related in a certain way. So we need to carry that relationship. But this is what we're doing in chapter 7. We're essentially just putting down a line that attempts to get as close to every point of data as possible. So that's where we're heading, the direction we're heading into next. Well, any questions at all, folks, with the construction of the scatter plot? Okay, here's a real tough question then. Comment on the scatter plot using the context of these data. This is really hard, not so much about the context. It's more, that's a new display for us. We don't necessarily know all the things we want to say. Nonetheless, let's give it our best shot. Any volunteers for something to say about this display?
The number of urgent increase, the growth rate decreases.
I think that's perfect. And that's the pattern we're seeing here in the data. Increase your grazers, you're going this way. Then you see this pattern. The net growth rate gets smaller and smaller and smaller. So let's say that here. As the number of grazers increases, the net growth rate decreases. Other things we might say, but it's not quite fair in this question just yet because we haven't looked in that vocabulary. But let's add this here nonetheless, kind of a preview to this problem so far. If this was a real question on a quiz or exam, then if I just say comment on the scatter plot using the context, that's perfectly fine because it's exactly what we did. But other things we want to say is, what is the form of the relationship? We could say it's linear because it appears you could put a line to it and it does a good job. So let's say here, the relationship is linear, other things we might want to say is, how strong is the relationship? That's a tough one to do on this display as well, but let's say it's a strong relationship. It is a strong relationship. But let me clarify both of those statements, starting with what I said right here, the relationship is linear. I would say definitely linear, but let's add some points on here to make it nonlinear. This is what a nonlinear relationship would look like. So let's assume these are all the data values that you've got. If your data looks like this, and for other contexts, you could get data just like that, this is no longer a linear relationship, because if you attempt to put a line through this, it does a terrible job. Here's the reason. In this region, all the dots lie above the line. In this region, all the dots lie below the line. Then over here, they're all above the line again. A line's not doing a good job. What you really want is a curve. Something like that would do an excellent job for these data. So if your data looks like that, we can't say linear, and it means we have to work extra hard to model the data. So good thing we didn't have that. We had, oh, didn't need to delete too much there. Oh, geez. Not too sure when I deleted that axis, but that must have been a while ago. So that's what we mean by linear. Any questions about that? Okay, let's clarify where we said it's a strong relationship. We might have said very, very strong. If we said that, that means the points would have looked like this. Almost exactly on a line. Our points have some spread to them, right? So I just said strong. You might have said moderate, or some people may have even said weak. It's all kind of qualitative now since we don't have the best tools. We don't have the correlation coefficient to analyze it. But this would have been an extremely strong relationship. If it looked like this instead, that would have been a weak relationship. A line still looks like it could do the job, but there's a lot of spread around that line of the points. So that would be a weak relationship. And what's even worse is if you have data that looks like this. Let's just take a preview. These data here, we'll come back to and discuss them on Monday, is like white noise. That has no relationship whatsoever. We wouldn't even call it a weak relationship. So there is nothing going on with this values. And the best way to model the data is just to find the sample mean y bar and just use that. A horizontal line, the sample mean, does the best job for these data, a cloud of points. So that's what no relationships would look like. This would be a nonlinear one, but these are nice, strong linear relationships, both of these. Between these last two ones, that point suddenly looks weird, right? Exactly. An outlier is any point that doesn't fit in a pattern. And well, when we say fit the pattern, it depends on how you display the data. An outlier here is a point that has, in some way, left a cloud of points. But watch out for this in the homework. I mean, this is a way out ahead. We are not too far in this section. There was a point that went way out here. And this is the display we're looking at. That one's not an outlier. It fits the pattern of the data being a linear relationship. Kind of weird in that case. That one's the outlier because it's way away from the main grouping. Well, any last questions, folks, before we call it a night? Quite a lot to talk about. Yeah, I'd say we'll practice the scatter plots a lot more, but think of the calculator scatter plots mainly to help with the homework, most of all. Any other questions so far? Okay, well, appreciate your all hard work. We completed week 6, so just about to midterms. Congratulations, everyone. Have a great weekend, and I'll see you all next Monday.
Variable rather than explanatory, would we lose on that?
Not at all. That'd be just fine. Thank you. Thanks, you too, Courtney. Thanks, Brandy. Thanks.
Hours, I know. That sounds so good. We're going to National Park here, it's our favorite. Well, our favorite. We used to go to the Mike's barbecue and the beef, but they sell something and they're just a little pricier. So we started going to the one, there's a new restaurant out by Seven and Ranch, I think it's called the Seven and Ranch Restaurant, I don't know, something. Where's that? Down Riley. And I've been there, but they opened this last summer. Yeah, I don't know how long they've been open, I think it's been a long time, but I've heard about it. We went there. Oh my gosh, we got like a full rack of those.